Back to the second week of our webinar on monitoring tropical storms for emergency preparedness. As we saw last week, we had an overview of tropical storms and their impacts. Today we are going to focus on monitoring tropical storm conditions during and after storms. Just a reminder here, and I want to point out this ARSET website for all the webinar material. When you go on this site, you will see both the presentation slides available, not just in English, but also in Spanish. So please, if you want to download them or later on, if you want to look at them, they will be there. There is homework there today, and you can find that on this site as well. You will have a Google form link through which you will be answering your questions. And more importantly, here is the information about certificate of completion. Those of you who have attended both the webinars and who complete homework assignments for both week 1 and 2, you will receive certificate. And it takes about 2 months to process everything, so please be patient, and even if you haven't not received after 2 months, then you can contact Marina Martins. She is the one who sends you certificates electronically. One more thing, all the webinars are recorded, and the recordings can also be found at the same site. So later on you can go back and view certain portions if you like, or you can look at the entire webinar again if you need to. So here is the outline for session 2. We're going to start with a brief review of last week's material, mostly definition about storm intensity, what are the impacts, major impacts, etc. Then we will go on to looking at data which help monitoring winds, precipitation, storm surge, as storm is right going to make landfall or it's right near your area or over area, which are the data sets that are useful. Then we're going to talk about flooding, monitoring flooding during and after storms. And this is very important for emergency preparedness, response and relief planning. And we're going to talk about a number of tools as shown here, extreme rainfall detection system, global flood monitoring system, the flood observatory or Dartmouth flood observatory. There is a near real-time flood monitoring and mapping tool based on MODIS data. Also synthetic aperture rate imagery that helps look at flooding. We will also see how to access those. And finally, we will have examples of NASA remote sensing data applications in tropical storm conditions. We'll also have demonstration of case study Hurricane Harvey. Last week, we already saw as Harvey was approaching Texas coast. We followed it using MODIS and WIRS imagery. We also looked at I-merge precipitation or GPM I-merge precipitation as the storm was approaching. Today we are going to talk about once the storm is on land, that's Harvey, how the flooding and storm surge, how do they occur, and how can we monitor those during and after hurricane. So that's how today is going to unfold. So we'll start from review session 1. We talked about different intensity, that tropical depression, storm, typhoon, and major hurricanes. They're all defined based on wind speed associated with them. And as you, from depression about 61 km per hour all the way to 178 km per hour for major hurricane. So these are the categories we talked about. And when you go to National Hurricane Center or Joint Typhoon Warning Center or Pacific Hurricane Center, you would see warnings or watch, and it says depression, storm, typhoon, hurricane, so you know what the strength of this storm is. And we also saw last week how damage occurs when wind speed goes up. We talked about this Saffir-Simpson wind scale, which is different hurricane categories, or these are the super typhoons. Again, from 74 or like 109 kilometer per hour all the way to greater than 252 kilometer per hour. These are the major hurricane categories. So basically, when you see a forecast with these names or categories, you know that it's the wind scale or wind speed that's going to be how much and how much damage it might cause. We talked about impacts of tropical storms, and we saw that Southeast Asian region and the Western Pacific region have substantial mortality because of storms and of impacts because of storm, also in America. So one thing to note here, that it's the storm surge and flooding on land because of rain, they cause major deaths. This is true for US for sure, based on data, and this is general experience everywhere else, that it's the flooding that really causes deaths and damage and destruction. And so that is why what we're going to do is, as we talk about storms today, we're also going to talk about flooding related to these storms, because that's how even after the storm goes, flooding remains there, and all the relief and response has to occur after the storm passes through also. So that's what we're going to focus on. We talked about how to monitor an approaching storm. We talked about precipitation data from GPM iMerge. We looked at the tool Giovanni. And this tool, we could animate data on daily basis. As the storm emerges, you find out that there is a storm nearby, you can start monitoring rainfall daily. And as it comes closer to the area you are, you can start monitoring half-hourly precipitation. And then we talked about GEOS 5 model, which provides winds and sea level pressure, not only in near real time, but also there is forecast. So you can see how forecast changes and keep monitoring as the storm approaches. We talked about, we looked at worldview, and Terra and Aqua Modis and SUMI National Polar Partnership VIRS. We talked about clouds and reflectance, how images show storm track or storm movement. And we also had a brief look at nightlight imagery, how power outage can be detected or using VIRS nighttime imagery. And we will see a couple of examples today how that can be used too. Then we talked about GDAX tool, which is Global Disaster Alert and Coordination System. That is based on satellites, models, media report, and this is very useful for looking at quick alerts. As soon as storm starts, it starts talking about it, and near real-time information has come in, you can see from this side. So we talked about this last week. And today now we are going to switch to looking at winds, precipitation, storm surge. And for this presentation slides, I'm going to focus on Hurricane Matthew. This was a major hurricane. There's a lot of damage, and some of you may have already known about it or were in area where you were influenced by Hurricane Matthew. In Caribbean also, and all the way to US, and in North Carolina, there was major flooding related to Hurricane Matthew. So we will use this case to see how different parameters can be monitored. So this dates were September 28 to October 9, 2016. But when you are in real-time situation, you can use the same tools and same data to follow a storm, or when a storm is in your area. Just look at this data to see what's going on. Again, this is operational centers we talked about last time, like National Hurricane Center, Central Pacific Hurricane Center, Joint Typhoon Warning Center. They provide early warnings for hurricanes, cyclones, and typhoons in different areas. They provide tracks, forecast maps, and probability of wind, how it's going to be, how much in what area. And you can see in here, this is again Hurricane Matthew, September 28 to October 6th. And what you see from National Hurricane Center, it shows how the track is, you can see starting from here, and here is, as you go forward in time, you can see the probability of area that gets larger. It starts from here, and then so this is general area that you would expect impact of hurricane to be. As it moves closer to land, you would be monitoring this for warnings, and then once it makes landfall also, you have this area where it is impacted. So this information is available from operational centers. But once you start seeing that a hurricane is here or it's approaching, we talked last week how to monitor rain and wind associated with them. Once it is there, you continue to use the same data like GPM iMerge and GEOS5 data to see how precipitation is and how winds are, what kind of sea level pressure. Lower the pressure of the center of the hurricane, you are going to have a strong wind or a stronger intense hurricane. So we will see iMerge precipitation here. This is again Hurricane Matthew. This is just similar to what we saw last time. It's an animation of daily precipitation between September 29th to October 11th. And you can see the storm moving in. It comes in here. It really played a big role in this area, and then it moved over the US. Haiti was really devastated by this hurricane. And so you can see the movement of this hurricane as it moves up, makes landfall, and then North Carolina, so South Carolina and North Carolina, they had major flooding because of this storm. And here, this is accumulated precipitation from October 6th to 10th over North Carolina. This is again using the Giovanni tool that we saw last time. And as you can see, this is in the total accumulation is almost like 200 millimeters for this in coastal region. It's a lot more even in interior. And I want you to notice Lumberton, which really got flooded. So if you are at any location, not only you start looking at iMerge precipitation every half hour, and also you can go to Giovanni and pick a point closest to where you are. In this case, we picked Lumberton, North Carolina, and here is the latitude longitude associated with this particular place or around it. This data are 1/10 of a degree, so it's about 10 kilometer resolution. So it is not super high resolution, but it gives you overall impression or idea of where major rainfall is going on and how it's evolving. So he just shows a picture on 9th October how much flooding there was. And by using Giovanni and looking at this one grid point and looking at the time series, this is from 8th October to 12th October, you can see that in millimeter per hour, rainfall was very high in the later 8th of October as storm passed through the area, and almost 30-35 millimeter per hour. And then it came down, but that's when the flooding occurred following this major rainfall. So if you're monitoring rainfall using iMerge, not only using Giovanni, but you can also see precipitation measurement mission website, and I just want to bring that up to remind you how to look at every half hour, latest half hourly precipitation. You can go in, like there's a storm here in southern Indian Ocean that you can see right now. So every half hour you can monitor, you can view past 7 days of animation, how rainfall evolved if you like. But when the storm actually is occurring, your main interest is in monitoring every half hourly rainfall in your area where you are. So by by looking at the images, and if you are more interested, then doing the analysis using online tool, you can keep monitoring how every half hour rain is changing, and as soon as you start seeing increase in rainfall, at the same time you will also experience winds outside, then you can start planning what to do following this rainfall, in addition to listening to all the warnings that you get from operational centers. So during the storm, you can still monitor all this data. Next is winds. So precipitation, which causes major flooding. In addition, winds not only have damages, but they also cause storm surge before the storm actually arrives over land. So this is GIS 5. We talked about this last time to follow the rainfall. But here is, last time we just saw maps of winds and sea level pressure. Here we also have access to this data. There's a little bit of work needed, but once you access this data, you can look at near real time and forecast winds and sea level pressure right at the area of your interest. So you can look at maps by going to this site, as we saw last time. You can do animation of winds and sea level pressure as well. But what we're going to see just is that how can you just access the digital data and then see. So this is the site where all the data sets are. You have year and month, and you have day. So you can pick 8th or 9th of October here for Hurricane Matthew, and then you have all the hourly data available from this site. So once you click on that, you can have either near real time or forecast data. You can pick month, day, and forecast also. So in near real time, you would just go to today's date, and then if you need forecast, you can pick appropriate file based on the hour and date and month. Once you go to the file, you would be picking a file name which has SLV, a single level data, which we are looking at surface, wind speed, and also looking at sea level pressure. So we want to look at SLV data, and you can go to this site to find out all about file name convention. But basically for winds and sea level pressure, it's the single level file is what, or SLV files is what you want to look at. And one more thing that we're going to use to see these winds is a visualization tool that's called Panoply, and that's available from NASA GIS. You can download and install this. It's a very simple step. You can go to this site, look at the version that's good for your operating system on your computer, and just download and install it in just a few minutes. And once you download this single level file on your computer by clicking on it, you can save it on your computer, and then you can use Panoply to actually visualize the data. Once you have Panoply, you can open these files, whether they are in HTF format or they are NetCDF format. Panoply can handle those. And so quickly you can plot wind speed and wind vector as shown here. This is on 9th of October, and you can see major wind speed was, this is shown here is in meters per second. Pretty large, as you can see, 20 to about 25 meters per second. And here is the sea level pressure in hectopascal or pascal. So the yellow part is about 998 hectopascal. So this is quite low pressure compared to normal. And so you can quickly just, if you are on the GIS 5 site, every hour you can see near real-time data, or you can download and use Panoply to actually be more quantitative to see how much wind speed will be there, or what kind of sea level pressure, where the center is when it's arriving on land, etc. So this allows you to monitor right when the storm is occurring. So Panoply allows you to do more detail over your own region. It can allow you to zoom in and focus, but otherwise you can just go to the site and look at the maps that they have on site, as we saw here. So either way, it gives you idea of how much winds there are, and there's also forecast. Very important thing is monitoring storm surge. So this is not very easy. A model has to be used in which a number of storm parameters have to be used, such as pressure, size of the storm, what kind of forward speed there is, what kind of winds, and track data. So these are all required. So here in the US, NOAA provides storm surge information, and that is based on a model called SLOSH, or Sea, Lake, and Overland Surge from Hurricanes. And here is the site. You can find more about the model itself. And here is the site where you would have a lot of information. The one that to notice is this P surge, or probabilistic hurricane storm surge. So that is what gives you information about how storm surge is going to be. So this P surge for Hurricane Matthew. And if you can see on left-hand side, you will see that there is how much probability there is that is given. Here's the percent probability of storm surge exceeding. You can choose it is exceeding 3 feet. Exceeding a height, you can choose the number you want here, and you can also have cumulative, and this is for Hurricane Matthew, as I said. You can see that this is here you can see that probability of hurricane is small. As you go here, a surge greater than 3 is shown here. Very high probability over here, more than 98%, that definitely storm surge will be about normal, greater than 3 feet. And then as you go up north, probability is going down. And this is just the time is shown here, what time it is. So you can, if you go online, you can also see a little animation, or you can look at what the maximum surge probability. So a lot of information here. So as soon as a storm starts, you can look at precipitation and winds and storm surge from this. If you are anywhere else in the world, not in the US, then GDAX is the site to use. And so Joint Research Center has a storm surge calculation model, and that is used to look at storm surge everywhere else. We will have a small demo at the end when we look at Hurricane Harvey. But here is where you can see that it says maximum surge. Again, this is in feet above normal. So 3 to 3.5, and then here is the height maximum. Here is also maximum surge Cyclone Hato, Hurricane Matthew. So this model can be used anywhere. So for storm surge, you will be using either NOAA or GDAX site, depending on where you are located, then you can monitor storm surge. Okay. So next, we want to talk about data which help in planning emergency operations. So last time we talked about shuttle radar topography, mission terrain data, and we also saw a site, GDAX, which provides you access to this data. So you can download TIFF images depending on where you are. You can click and see. We also saw CDEC last week. This is a socioeconomic data site that provides population density, roads, other infrastructure data. And this is an example of during Hurricane Matthew, and this is North Carolina again. The brown square here that shows SRTM terrain data, and the heights in vertical meters are shown here. So here obviously there is higher grounds, and then here as you go, the terrain goes lower. If you can zoom in, what I've done is taken terrain data as well as population density data, which is in given here, and this is population per kilometer. You can see that these are the urban centers, and I've taken all these data into a QGIS platform. So you can either just look at the maps online on GDEX and CDEC, or you can get the data beforehand, even when there is no storm in your area. You can get SRTM terrain data, and if you can zoom in, you will be seeing features where you have topography. You can, using GIS, you can also calculate slope and see where there is lower slope or flat areas surrounded by high terrain area, probability of flooding will be more. So before even flood starts, these data can be looked at, so you already know where the major population centers are, what kind of slope within the city that you can expect where waterlogging might occur. So when rain starts occurring, you can actually expect where there will be more flooding and where more people will be needing help or rescue or warning if it's not that strong storm. But these data are also very useful for emergency planning, and they are available freely online for you to download even before actually any storm occurs or any emergency occurs. Okay. So we talked about during and even after, these are some of the tools you always use to monitor a storm. So winds, precipitation, storm surge, and the additional data like terrain and population. So in the beginning, we saw the impact is mostly in terms of flooding. So either because of storm surge or also because of rainfall over land. So it helps to see where there is flooding going on. And so we're going to talk in some detail about different flood monitoring tools. Okay. So remote sensing based flood detection can occur in 3 different approaches. As shown here, the first one is detailed hydrologic modeling that can provide you stream flow and runoff over ground. So how much water there will be on ground because of precipitation. Not just precipitation, but depends on soil moisture condition, terrain, so a number of parameters. They decide how much stream flow or runoff there will be, and quantitative information can be derived by using hydrologic modeling forced by weather data. So that's one way. Another thing is inferring flooding based on precipitation, so that you have long climatological record of precipitation at a location. When you keep monitoring precipitation, it exceeds certain level, then you know that there will be flooding based on past data. And so that's inferring flooding based on precipitation. So there's no modeling involved. It just looks at the data and looks at the past data. And so that's one way. Another thing is to look at just land surface and then decide whether it's dry or wet. So we will see a tool that uses optical data. It looks at land surface, and then it can detect when there is inundation on previously dry surface. So these are three approaches that NASA tools use to look at flooding in different ways. And it's important to note that a lot additional information is needed too for these flooding tools, but these are the basic principles, either rainfall or it is looking at the surface. Okay, and ARSET had a detailed webinar, advanced webinar of flood monitoring, and here's the link that if you want more information about these tools and how to monitor flooding, you can always go back and look at these webinars. So we're going to look at precipitation-based flood tools. And first of all, there is one tool that we will see. It's called Extreme Rainfall Detection System, or ERDS. This is the second type of flooding tool that it infers potential flooding based on GPM iMerge data, the iMerge data that we've been talking about. And then there is another tool, which is the first kind, which uses hydrologic model and rainfall to give stream flow and runoff, that is Global Flood Monitoring System. GFMS uses TRIM, Multi-Satellite Precipitation Analysis, or TMPA. We talked about this product last week. You may want to review it. The TRIM was the predecessor of GPM, and with TRIM data along with other constellation data, we have multi-satellite TMPA data at 25.25 degree by 0.25 degree latitude longitude, or 25 kilometer square data. GFMS uses that and provides a hydrologic model, and then you provide stream flow and runoff. GFMS will also be transitioning to iMerge soon. Once we have like long TMPA iMerge data, combined data available for more than 20 years, we talked about this last week. Okay, so we will start with a brief review of Extreme Rainfall Detection System. This actually was developed by Ithaca Web. Here is the website, and this tool is for emergency preparedness for World Food Program. This is the UN program. And so what it provides is quick alerts. It uses near real-time GPM iMerge data. We saw that available from Giovanni or PMM site. Every half hour it is available. In addition, ERDS also uses NOAA Global Forecasting System, rainfall. So near real time comes from iMerge, and there is forecast component that comes from NOAA GFS, and it provides alerts of potential flooding where there could be, because of extreme rainfall, there could be potential of flooding. And it uses rain gauge data, or Global Precipitation Climatology Center land-based rain gauge data to decide whether near real time or forecast rain is going to be much higher than long-term mean data, and based on that, it provides alert, as shown here. The red areas, these are all based on precipitation. That's where potential flooding is. Okay. So as shown here, it provides cumulative precipitation. The one that's shown here in light colors is precipitation. In near real time, it is from iMerge. And if it is forecast, then it is from GFS, and you have a way to choose it. You can look at accumulated rainfall from iMerge from last 24 hours all the way to about 96 hours, and you can go forward from GFS and look at precipitation. And based on that, alerts are provided, and as you can see, these red areas is where there is potential of flooding. This snapshot, of course, was taken on 15th of April, but we're going to look at this site, a demonstration at the end. We'll see how ERDS can be used to quickly look at near real time as well as forecast rainfall and where the flood potential is. This is somewhat an experimental product, because that has also switched from TMPA to iMerge. So it's important to do local verification in the sense that when there's a lot of rain in your area, you can go to ERDS and see how closely it matches your experience on ground. But generally, the alert areas are pretty accurate, that it provides that, okay, here is where there is high potential of flooding because of rainfall. So this is ERDS. This is available in near real time and forecast only. The next tool, Global Flood Monitoring System. This has not only near real time data, but it also has archive data based on TMPA. So this, because it's based on TRIM, it provides data between 50 south and 50 north. That's where we are interested for tropical storms. It provides multiple parameters. It provides instantaneous rain rate for 3 hours, can accumulated rain rate for rainfall for 24 to 168 hours, which is 7 days. So you can look at changing rainfall accumulated over different time period, which causes flooding. And stream flow rates and flood intensity are derived at about 12 kilometer resolution. Also available at 1 kilometer, but that is more or less in near real time, this short time. If you want to look at a long-term data, 12 kilometer data are available. And this tool is available since 2013. So at this point, it's important to note that we talked about this last time, that TRIM satellite is no longer flying, but based on past TRIM climatology, there is calibration derived for other national and international satellites carrying microwave sensors. And they are calibrated with TRIM data. And so the TMPA continues because quite a few applications used TMPA. So until they all can switch to iMerge, TMPA are being available. And so that is being used for GFMS. It uses TMPA plus. There is a model, GIS model that we've been talking about. It also is used for reanalysis, in which satellite data are assimilated and near real-time data, weather data are available. That's called MERA, or Modern Era Retrospective Analysis for Research and Applications. So MERA data provide winds, soil moisture, a number of information, and then variable infiltration capacity model is used to get stream flow and runoff. There is a runoff routing model, and there is a reference provided here that provides details, how the model is set up and what kind of routing scheme is used to get stream flow and runoff. Also, ARSET also had a webinar on WIC, so you can go back to the site and see what is involved in getting stream flow from variable infiltration capacity model. So we are going to have a demo at the end of this site, but basically it provides capability of zooming into any region by using zoom in and zoom out feature. You can pan the map and go to a particular area. You can select area. Not only that, any 12 kilometer grid is, you can choose by latitude and longitude, and you can choose particular time range between which you can monitor flooding. There is near real time and past. You can pick start time and end time, and you can animate and see how stream flow and runoff they change. Here is where you can pick different variables. Most important is flood detection depth. So it provides depth above a threshold in millimeters. So higher it is, stronger the flood is, and we will This is the example for Hurricane Matthew. We'll see that for Hurricane Harvey at the end. This is 9th October, 12Z. You can see here is after the storm has hit this area, you can see where there are flood depth exceeding more than about 200 millimeters. There are locations where 20 to 50 you see many. There are some where about 100 millimeter exceeds flood depth. And so this allows you to look at, zoom in and look at any location, any one pixel, and see how actually flood depth changes. So you can, this is for past, but in near real time also, you can get the same information. So we talked about ERDS and GFMS. Both are rainfall-based flood detection tool. In one case, you just get alerts based on rainfall. In this case, you actually get flood depth, intensity, and you can also see this green area, which is runoff outside the river channel. You would see that's where you would expect flooding to occur. Okay. Next, we talked about land cover-based flooding tools, and they are, the one that we're going to talk about is based on MODIS. MODIS, we talked about this satellite. It's a moderate resolution imaging spectroradiometer with many, about 36 spectral bands. But you can see from this chart here that when you look from the satellite, and when we looked at worldview and we were monitoring storms like Harvey, we saw that clouds you can see ocean, you can see land. And so MODIS allows you to see soil, vegetation, and water in different spectral bands. And so this is being used to detect where there's flooding going on. So there are two tools. That is MODIS near real-time flood mapping, and there is Dartmouth Flood Observatory or the Flood Observatory. It uses the same information with some additional data to provide flooding information. So what is done is that MODIS data, for a long time, they're used to detect permanent water. And then as flooding occurs, the heavy rainfall occurs, or a storm passes through, then you can see that the difference with that, that permanent water can tell you areas where there is no permanent water, but there is temporary water resulting from flooding. So here is an example. MODIS, this is the Mississippi River flooding in 2016. This is March 15, and this is May 13. And you can see the clear difference as the flooding changes or river level or width changes. So you can look at images and figure out where there is inundation going on. To note here is that you do not get stream flow information. So you're not getting information about how river is flowing faster or how much flooding there is within the channel, but it's the area outside the water bodies where there is water, either water logging has occurred or there is spilling of water because of flooding, that is detected. And that is very useful for planning relief operations or to see which land area are flooded because of heavy rain or because of overflowing rivers, say. And these are the bands used to derive this flooding. One thing to notice here, so that the major advantage of this is that MODIS provides daily observations. So you can, twice daily in many cases, so you can monitor surface inundation nicely. And it's a global data, so you can use it anywhere. But one thing is that it's an optical sensor, and it cannot see through clouds. So if there are a lot of clouds, as we saw last week, we can look at clouds and and see where the storm is moving, but what's going on at the surface is not very easy to see when there are clouds. So if there is very thick cloud cover, which usually there is in hurricane, you may not be able to see flooding going on right underneath, but as the storm passes, usually there is clear sky right behind it that tells you where there is still flooding going on. So this tool, if there are gaps in the clouds, sometimes you can see through some surface flooding, but this is very useful to look at post-storm flooding. You will see in a demo at the end how you can see which areas are waterlogged even after the storm has passed. So here is the website where this near real-time and past flood mapping is available from Moody's. It's available at 10 by 10 degree grid tiles as shown here. And there are, it's a 250 meters resolution, and there are 3 types of composites available: 2-day, 3-day, and last 14 days. So so many days composites are available. That helps in eliminating some of the effect of clouds. So even if it is cloudy for 2 or 3 days, you can always see last 14 days and see how flood frequency changed, and that gives you indication of where there may be inundation going on. So this is helpful. Once you click on any of this grid, you can look at permanent water present in that grid area. You can look at flood maps in that area, and we will see that at the end for Hurricane Harvey, how to see that. And then there's one thing to notice here is that not only when there are clouds present, you don't see the surface, but if there are broken clouds, and even if you are looking at some surface, there can be some cloud shadow on that land, and sometimes that can be misinterpreted as inundation. Similarly, if there is a terrain in the grid area that you are focusing on, then terrain shadow can also be misinterpreted as surface water. So there is improvement going on constantly to eliminate these effects. But sometimes still you might get these effects in the data, so you have to be careful with that. But more or less it does help you look at general area where inundation might be occurring. So this data are available since 2013 also. So you can look at present and past data to study how inundation patterns are in your area of interest. So this is just a showing what products are available and in what format. Flood map, just image is available. Flood water is available as KMZ or shapefile that you can use with GIS or Google Earth. Permanent surface water is available, and all these parameters are available at GeoTIFF as well. There is a lot of information on this site, and there is documentation and papers that you can get more information about the tool itself. This is again North Carolina, Hurricane Matthew. This is October 10 to 12. This is just as hurricane passed through the area, again focusing on North Carolina, and you can see this red dots here. If you zoom in, you can take it in as KMZ file or a shape file in GIS and really zoom in and see which streets or which areas are flooded. So it also helps look at coastal flooding. So we know we have information about storm surge, and Moody's also can detect when there is flooding going on. If not right when the storm is passing, as the storm passes and clouds clear, it can clearly show the surface where there is inundation going on. So this is a useful tool for post-storm planning, that where the flooding is occurring or where there is water logging for a long time after even the flood is gone. Another tool again uses MODIS information is the flood observatory, and here's the website. Similar information is used. It provides near real-time and current and past flood event mapping, and here it highlights red areas where there is inundation occurring. It uses both MODIS and local in-situ data also they use, incorporate in. There are also other satellites such as Landsat 8, EO1 for past data, it's no longer available, but then there is Esther flying on Terra. These are all satellites and some instruments. They provide similar information to MODIS that is used to look at whenever these satellites are overpassing some area and information is available, then that is also displayed. Also included is Cosmo, SkyMeet, and Sentinel-1 radar data. They are also used to look at surface inundation. These are MODIS is daily data. These satellites don't provide daily data, but whenever they are available, they are included in this. And there are multiple data sources used. So even GFMS and iMerge and TMPA information is available from this site. This shows flooding due to Hurricane Matthew, and this is 14-day composite from MODIS. And you can see all the red areas where there is a lot of flooding going on. This is in Haiti, when hurricane occurred, you can see where the Hurricane Matthew passed through this area. You can see SAR data. This is from JAXA's ALOS pulsar data. And so whenever different SARs are available, you can see the flooding also. So this is MODIS, this is a SAR. So synthetic aperture radar, I mentioned here a couple of times SAR, but some of you may already know what SAR is, and you may have seen the data, but it is something that is going to be like future sensor if you wish. It's a synthetic aperture radar, it's an active sensor. So most like MODIS or GPM data or what we talked about, REARS, these are all passive instruments. SAR is active. It's a radar that throws frequency on ground and then collects backscatter data, and then that backscattering signal depends on what the surface is, how rough it is, how smooth it is, what kind of terrain it is. It can bounce back and forth and then go back. And so information of surface is contained in that backscattered data. And so different frequency bands are used these are the microwave frequency range, and they are used for many different applications. And looking at surface, especially for flooding, is something that it's useful. In addition to, there are many applications in agriculture to look at soil moisture, biomass, also looking at deformation because of earthquake, you can see from radar. And so this is, there are many applications. Currently, these are new, and these are the future satellites. So you can see that some are not freely available, but these are all the old satellites ended. But now there is Sentinel-1 that is available starting from 2014, and these are also available, like these are the future one, NISAR and biomass planned for 2021. So one advantage of SAR data is that it can see through clouds. So unlike optical sensors such as MODIS and REARS, even if there is storm going on and there are a lot of clouds, surface can still be seen from SAR. And among many applications, disasters monitoring is very, very useful. As you can see, here is where there's open water. So, and that these are the classification of land. You can see not inundated surface, there is blue is the open water and yellow is the inundated vegetation. Okay, so that's where the water is right here. So looking at SAR images, backscattered images, one can see where there is water on ground. So Sentinel-1 SAR images are freely available right now. They're available from Vertex. This is in Alaska. This is an Alaska satellite facility. They provide SAR data freely. There is a tool. It's called Sentinel Application Toolbox or SNAP. This can be used to actually process these images. It's a little advanced training, but as you see, ARSET did provide an introductory webinar about our background about SAR, and you can find this information at this link. And there's going to be a more advanced webinar in July of this year, so that you can look at learn to analyze SAR data, how to obtain the data, how to analyze image. Why we're talking about this is because as we move forward, as you know, more SARs will be available. Right now, Sentinel-1 data are available maybe every 12 days, but as we have more SAR carrying satellites going up, we can have more frequent data, and that can help see through clouds and look at flooding even when there is storm going on. So this is something to keep in mind. This is an example. It shows before and after Hurricane Matthew. So this is a RGB image or red, green, blue image. The way it is done is that backscatter data before hurricane passed and after hurricane passed, different backscatter data are used, and then the color scheme is used so that this red or this orange area is where there is flooding going on. The blue one is where the permanent water is. So even before storm, this water of course was there. But as the storm passed, you can see where inundation occurred. So this is coastal inundation, inland also you can see areas, all these orange areas, they show where there is surface that is flooded. So SAR images can quickly tell you, in addition to MODIS, where flooding is going on just by looking at the surface. Okay, so this brings us to some more examples where NASA remote sensing data are used. So we talked about monitoring data in near real time and in forecast mode. Also look at flooding in near real time. And then we're going to have some examples and then demos. So here's in one example where different resources from NASA were used by FEMA after Hurricane Harvey. Here, as you can see, after 25th was the landfall day, and then after that, FEMA included SAR for looking at flooding, and also requested to send a SAR on unmanned aerial vehicle. Here is where constant monitoring goes on using NASA satellite data. So MODIS and VIRS, they show how clouds are moving in, spiral bands because of storms are moving in where there could be rain. So there's also flood monitoring using Cosmo SkyMig. This is from a European satellite, and Spot 6. So these data are available from NASA Marshall Space Flight Center showing flooding. And so there is remote sensing products from NASA. They're available on FEMA FTP servers. So FEMA does use satellite data to monitor in near real time and also planning for post-storm flooding monitoring, optical data, also using SAR data. And here is where all the data are if you go on this site that we talked about. Here is another example. This is changing vegetation detection, and then over Puerto Rico, that is after Hurricane Maria. This was in September 2007. So top figure shows pre-Maria image from Landsat satellite, and you can see all the greens, which is where all the vegetation is. Middle figure is post-Maria image, again from the same sensor on Landsat 8. And what you see is that there is heavy impact, that a lot of vegetation is destroyed, and all the brownish area is where there is really no vegetation left. So as the trees fall down or the vegetation is damaged, it can be seen from this data. The bottom figure is the non-photosynthetic vegetation, so that is mostly exposed wood and surface litter that you can see from the satellite. This is also post Maria. So this is how you can quickly look at image and figure out what is going on. This is something we talked about earlier. This is the nightlight imagery from VIIRS, flying on Sumi and PP. And you can see this is again Hurricane Maria over Puerto Rico. These are the areas where urban centers are, and you can see lights at night. This is the baseline before Maria. You can see this. And just after the passage of storm, if you look at this area, you can see the intensity decreasing wherever. So you can see, if you can zoom in, you would know where image went dark or where the power was lost. So this is a quick way of looking at power outages because of storm. And so here is a comparison, like you can see baseline and after. If you zoom in, that where there was, here is where there is major power outage. You can see before a lot of lights. Here also there are areas like this area had less intensity. You can see here. This area also had power loss. And so just by looking at images, comparing it to before storm, you can quickly see where power outage is. So that's where repairs are planned quickly, or if there is any help needed, it's provided. So this helps in planning for response to the storm. Okay, here is yet another example in which iMerge precipitation was used to track cholera risk after Hurricane Matthew. And it's a lot of information, but top is basically showing increase in precipitation due to Matthew, and then here, based on that, severity of cholera risk is given. So, and this has been validated with data on ground that this precipitation from iMerge does help looking at post-storm health risks such as cholera in this case. So this brings us to the demonstration part of today's presentation. Now we're going to look at a case study of Hurricane Harvey. Last week we already saw iMerge animation showing precipitation as the storm was approaching. Today we also saw how rainfall occurred as Hurricane Matthew passed in, and so we also saw sea level pressure and winds from GIS 5. We saw clouds from MODIS. So the focus of today's demonstration is mostly on flooding, because now you already know how to monitor other parameters, but what causes a lot of damage and what requires a lot of response is really flooding that occurs because of either storm surge in coastal region or inland because of very heavy rain. So what we're going to do is use Hurricane Harvey as a case study and look at global flood monitoring system, MODIS NRT system, and see GDAX, how storm surge changed due to Harvey. And so we will do that. Before we do that, however, though, I want to show you extreme rainfall detection system, which does not have past data, but it's a useful tool for near real-time monitoring. So I'm going to switch to a demo mode. And start with extreme rainfall detection system. This is the near real-time alert system. On the right-hand side, you can have information about which day and time you're looking at, which is the last analysis you're looking at from forecast. And here you have near real-time rainfall information, cumulated forecast, and there are alerts in near real-time and forecast. So let's see if we look at cumulative near real-time. So this is a near real-time 12-hour, last 12 hours, last 24 hours. And you can, of course, zoom in and out. And this is a storm in southern Indian Ocean already. So these last 96 hours of rainfall from iMerge that you can see. You can save the images. And here is the color scale for amount of rain in millimeters that you can see. So this is about, the color green is about 150 to 200 millimeter accumulated rain. Here it is more like 250. Similarly, you can go to the forecast, and this is forecast for next 24 hours, next 40 hours, all the way to 48 hours to 144 hours. This is based on GFMS, the rainfall. Okay? And based on that, you can see alert, near real-time alert. As you go down, if you see any red area like here, you can zoom in and you see there is a red area where ERDS is saying that there is potential of flooding based on cumulative rainfall. So this is based on last 96 hours of rainfall. You can see where all the red dots where there is flooding likely or this alert is given. And similarly, you can have from forecast. You can zoom out and go to different regions and see where there may be flooding like here. You see in Uruguay, the forecast of flooding you can see. So this tool is useful in looking at near real-time and forecast flood areas where there is going to be flooding. So that these alerts are given. So first stop when any storm occurs is really the operational hurricane centers. Then next you can look at all the data from iMerge, GEOS 5 forecast, WorldView, MODIS images, and then for flooding, then ERDS provides near real-time information. There is information about half-hourly rainfall here that can give you indication where the flood might occur. And then there is global flood monitoring system. So you already have seen this before, how to zoom in and zoom out and look at the rainfall. And here is how you pick different parameters. You have accumulated rainfall, stream flow. We're going to look at flood detection. That is the default that you see here. And I'm going to show you a little animation of stream flow that we did because of Hurricane Harvey. So I basically zoomed into the Texas region. This shows data in April, but you can change the dates. You can zoom in and zoom out and pan the map using the panel in the side. And here is where you see all the rivers. You can change the start time and end time. We're going to look at Hurricane Harvey. So 25th of August was when in 2017 when it first arrived overland over Texas. And here is the depth above threshold in millimeter. You can animate. As the storm passes, you can see how this runoff and stream flow are shown here. Here is the area where the flooding depth is above threshold by 50 to 100 meters. In some areas, as the storm moves 28th of August, you can see almost more than 100 to 200 millimeter above threshold you can see. So generally, the green area is where there is above threshold runoff, and then there is rivers which are flooded, and so stream flow is shown here. So there is possibility that there is riverine flooding affecting nearby area as well. So this is how you will be able to look at flooding based on GFMS. This is based on hydrologic model and rainfall, so it's not affected by clouds. So even when the storm is coming in, you can start looking at near real-time data. As you see here, the most recent data will be available when you go to this site. You can zoom in and see what kind of flooding is occurring. Every 3 hours, you can monitor based on TMPA data. Later on, though, based on iMerge, this data can be available at more frequent time. There is also a short-term flood forecasting based on GIS 5 data, and so you can change the date to see forecast of how things are going to evolve, where there's going to be more stream flow or flood above that threshold. So intensity of flood can be seen too. So this is GFMS. Next, I want to show near real-time MODIS flood mapping. This also has past data, but you can see that whichever region there's a storm that you're interested in, you can go right to that area. And once you know from the MODIS imagery, looking through worldview and also looking at iMerge data, that storm has already come ashore, you can start looking at the region of your interest. In this case, again, as for Harvey, we're going to look at Texas. You can click on the grid, and this will have most recent available image. We're going to move back to 2017 to go to Hurricane Harvey. And you can change. These are Julian days, so year, day of year, so you can change that to go to August of 2017. And what you see here, this is 8th of August. We know that 25th of August when Harvey came ashore. And so following that in GFMS, we saw that flooding started occurring and it increased around 28th, 29th, even 30th. And so I'm just going to pick, say, day 28. You can zoom in. Because of clouds, you may not see very much flooding going on at 2 or 3-day composite, but you can use 14-day composite. So here is the blue areas they show permanent water, but now you can see this flood occurrence, and that's where you see where the flood's occurring, and you can zoom in, and we're going to look at even in more detail. So you can quickly look at the image, or you look at flood water as KMZ, or that is a Google Earth You can download shapefile or TIFF file and look at, get that in GIS. But in here, what we are doing is just using Google Earth to just quickly look at the image. And when actually storm is on the area, this seems like a good strategy that you quickly look at the Google Earth. And now you can zoom in and see where there is inundation. This is 28th of August. As you zoom in, you can see this is Houston. As you zoom into areas, you can see the streets or neighborhood that are flooded. This is 250-meter resolution. But as you zoom in, you can see here is where there's flooding going on based on MODIS imagery. So this is a quick way of identifying areas. If you download this as shapefile and look at it along with terrain or slope data in GIS and again population density, you might be able to decide where immediate help is needed. But this is again, sometimes even if there is flooding going on and clouds can't see, post flood, when the clouds clear, you can, wherever there is still water left in as on the surface, you can identify those areas based on this MODIS image. So this was Hurricane Harvey as it affected Houston. You can see several places where an inundation, you can zoom in and see which roads have potential of being flooded at this time. And that's where you probably want to plan some relief or provide warning for people not to go there. So this helps during and past storm flooding detection. So it's a useful tool. It's a daily data. And you can quickly look at Google Earth engine, look at the KMZ file to see where there's flooding going on. We're looking at past data, but this can be available in near real time, so you can see this. So this is MODIS NRT. Finally, we're going to look at storm surge. And I want to take this opportunity to go through GDAX. You can see this tropical storm, Flamboyant, in southern Indian Ocean that's occurring now. But if you go to alerts, so you can, any near real-time storm you can see here, you can click on it and you can get information about that storm, like summary. You can see name, date, countries affected. This is offshore, so no people are exposed, but you can have information about the storm. If you want to look at the past storm, alerts is where you would go and search for the alerts, and you can pick cyclones, and you can also pick days and months. So we are going to look at August 25th, when Hurricane Harvey was. And here also we can go to, say, 30th. Okay, so this is the date, and then you can submit, and that gives you, here is Hurricane Harvey. You can have full report. So this is how you will find past data, but in near real time you can go right to the site and find it. Here is where you have information, which countries affected, how many population was exposed, wind speed, how much was that, and maximum wind speed was 230 kilometers per hour. This was category 4. Maximum storm surge 1.6 meter on 26th of August because of that. And still vulnerability was considered low because there was, if it were somewhere in country which is not prepared or not developed enough to respond quickly, maybe there is vulnerability is large. And so this information can be obtained in near real time as well as for past data. But what I really wanted to point out was resources. Here is where you can find storm surge data. You can download these files. This is the location, and this is by hour. This is based on the JRC model that you can see data, but you can also see so much other information such as extreme rainfall associated with the storm based on NOAA data. And here is the storm surge. You can click on it and it shows animation. This is 26th of August. And as you can see, the storm is moving and then the storm surge is changing. This is feet above normal. And so you can look at this animation to see where storm surge is going on, and also if there is, what is the maximum storm surge height. So that is shown here. Again, based on the model and observed data about winds and track and size of the storm and pressure. So the main purpose of showing this was just to give you an overview that you will see resources from different sources, so to say, and you will also have storm surge information here from JRC model related to tropical storm. So this is the way to look at storm surge when storm is almost there, and you will see a map like this where it shows where the rainfall, how it changed, the track, the areas affected, the flooding, the population affected. You can zoom into this map and you will get the entire report about the particular storm. So this is just for your information that you can look at what the flooded areas where the storm surge was. So this is a summary very quickly given about a storm. As the data come in, they start putting in. So this is a useful tool. This uses NASA data, especially from MODIS and iMerge, and they are used in here. Okay. So we saw GFMS, we saw MODIS NRT, and we also saw GDEX to see storm surge, where you can see different storms, how to monitor flooding related to that. Earlier we saw how to see other parameters associated with that, such as clouds, rain, winds, sea level pressure. So in these 2 weeks, I think the overall idea was to present all the resources available from NASA that can help monitor storm before, during, and after, and especially focusing on rainfall and flooding, how to look at storm surge. And so here's a brief summary of what we saw in these 2 weeks. So NASA remote sensing and Earth system model data that we saw, they augment operational tropical storm data. So NASA is not doing operational forecasts, or it's not an operational center, but all the research quality products that are coming out of satellite observations and models, they are very useful in augmenting already available information from operational centers. So once you have warnings and watches from these centers, you know the probability of winds or track, then you can look at NASA remote sensing and modeling data to get more information. During initial phase, initiation of, then propagation, and also dissipation stage, you can see from remote sensing data. So not only remote sensing provides an overall perspective, you can look at an image and you can see where the storm is and the surrounded area. It's a continuous spatial field that you can see, as we saw in many images. And you can also zoom into a given location, like we did in North Carolina for Hurricane Matthew, or in Houston for Hurricane Harvey. You can zoom into a particular area using these tools and look at winds and sea level pressure or precipitation. You can look at MODIS and WIR's true color imagery using worldview, as we saw. Finally, you can look at river flooding and surface inundation from all these different tools that we just saw. That gives you idea of where the flooding is and where quick response might be needed. You can look at nightlight imagery, again, from worldview, and see where there is power outage. We saw an example of Puerto Rico because of Hurricane Maria, how dramatically you can see power outages compared to a baseline or earlier image. And we also saw that storm surge information is available in the US from NOAA and from JRC, this Joint Research Center, from GDAX. So all these resources are there to look at storm in different phases. So storm-related emergency, so preparedness and mitigation earlier, response relief, they all can benefit from combined use of all these data that we just showed. Weather data is there, flooding data, terrain, socioeconomic data, also storm surge data. So combination of these data and tools can help you in preparing how to respond to the storm emergency. Here is something that is from FEMA, that how would you prepare for a storm? What would you do now that when storm is approaching? During the storm, so you prepare, survive, and then be safe afterwards. So these are the steps that FEMA recommends, which is true anywhere in the world where storms are experienced. And what this shows is that NASA remote sensing data can help in these phases. We saw rain, winds, and flooding monitoring. You can look at low-lying area. You can look at flooded streets and roads. You can monitor flooding afterwards and see where there is still water present on previously dry surface. You can monitor power outages during and after the storm. And so all these decisions can be based on some of the data that we talked about. What is important is that all these data, like GEOS5, TRIM and GPM, TMPA, iMerge, MODIS data are available. It's a long time record. Historical data are available. And so actually preparedness and mitigation, this data are very useful. These products can be looked at in your area for past so many cases of storms, and that can help in deciding emergency response strategy based on past data, and then when near real-time conditions occur when a storm is coming up, you can use that experience from past. So combining in situ data of damages, about flooding, about destruction from the past, and remote sensing and modeling data and socioeconomic data from NASA from the past, you can develop strategy for how to respond to a storm in near real time and also plan for future based on your past experience. So it's not just near real time information that is useful, but it also helps to look at past cases in your area and all these data to understand how storm conditions affected the area you're interested in. So there are some obvious advantages we talked about of remote sensing, that it provides global coverage. If you have just a few rain gauges, then you have very limited spatial flooding, or stream gauges provide just here and there limited information. If you have remote sensing, you have continuous spatial coverage. These all data we talked about are open source, and there are tools which help you access data, subset it temporally and spatially. You can analyze online, you can visualize online. You can also download and do further processing with GIS or hydrologic modeling, as we saw. So it's convenient that way. And since we have past data, they can help you in developing strategy for current and future storms. One thing to notice, though, is that these are all research quality products and not operational products. So usually it helps if you validate in your own region, looking at past cases, uncertainty, if there is any, you can figure out, you can remove bias based on your in situ measurements. So that way, one recommendation is that look at the data in past cases in your region so you know how to interpret it in near real time and even for future. One limitation, if you consider it, it's that all the data we saw, they have different spatial and temporal resolution. So if you just look at data by using some of these tools and visualize it, for qualitative purposes, it's fine. You can look at the images and interpret and derive information and see how you want to respond to emergency based on that. If you want more quantitative information, then there is further analysis needed. So you probably want to download data for your region. You may want to regrid it at certain resolution using GIS. You can also use hydrologic model if you or people use urban flood modeling or storm surge modeling. So data can also be used for more quantitative studies. So both ways these data are useful. Just qualitatively, you get images and decide what to do, or have more quantitative studies where you actually look at digital data with other tools and have more quantitative decision making, like they have in ERDS, say, for example. So this brings us to the end of this webinar series. I hope that in these 2 weeks, we provided information that will be useful to you, especially in dealing with tropical storm-related disasters. And we really want to thank you for attending this series. And what we're going to do is we have a discussion session following now. We have a few questions. We can also take a few minutes to explore some of the tools that we talked about if you like, and we can have question answer session after that. So thank you again. So before we go to the question answer and discussion session, just a reminder here that there is a homework 2 that is posted on our ARSET site, and the link you can see it in the chat box, and it's due by 31st of May. So just a reminder that you complete homework 2 by that date. Thank you again for attending this webinar. If you have any questions or if you want to look at any tools that we talked about, again, here is the reminder for the homework again. This homework 1 and 2 both are given on ARSET website. And first homework is due by on 24th of May, and the second one by 31st of May. And it is required that you complete both these homework in order to get the certificate of completion. So there are other webinars on the ARSET site. All the training materials are there, slides are there. If there are case studies or exercises, they are also online. and you can see past webinars such as WIG that we did earlier this year. One more request we have is about your feedback to this webinar series. Next, you will receive an email with SurveyMonkey link. Shortly you will receive that. And when you receive the link, please go through the survey. It's anonymous, but it's extremely important to us at ARSET because that helps us to know what you liked about this webinar series, how can we improve, what additional information we can provide, what other topics you are interested in. So there are many questions related to that, and so it will be great if you can respond to this survey. And again, it's anonymous, so you will shortly receive a link and then request that you finish the survey. And that just to help us, your feedback is very important to us. Before we end, we open today's session for question and answer. There are two points I want to make. One is you will see on my screen there's a site that shows NASA's mission Cygnus. This is a experimental or research mission which we recently launched. There are 8 little satellites in the orbit, but they are for observing hurricane-related winds, especially over ocean. And so they provide narrow tracks over hurricane, but you can get information in detail. You can go to this web page and get information about this mission. You can also find that Cygnus wind data are available from this site. Here is where you can find data products. And so basic ocean surface wind speed derived from Cygnus can be found here. Since this is not an operational mission, we did not go into great detail, but this is just for your information. In addition, there was a question earlier last week about how to get digital data, and I want to leave you with this site. It's NASA Earth data site, and you can search data, find data, or you can visualize data. But here you can actually enter name of some product that you're interested in, and then it finds matching data, and then it actually you can click on it and find more information, and it allows you to download this data. So this is a general search engine for any NASA data. So with that, we would like to see if you have any questions for today. We already have a few questions here. One is about, do you use other high-resolution terrain besides SRTM? So here in the US, there is national elevation data. It's 10-meter resolution, but I am not familiar with any data low resolution SRTM available globally. If you have used any such data, then please mention it. Also, there are for urban flooding or for high-resolution terrain mapping, LiDAR are sometimes used. These data are not always available. They're very high resolution and they're not available to all. People fly LiDAR to get higher resolution terrain data. In airplane, they can fly LiDAR. That reminds me to mention here that ARSET is planning a webinar on urban flooding. So urban flooding is a special case by itself because it depends not just only how much rain there is flash flooding or there is storms or sustained long-term rain. Or there can be multiple reasons, but because of the resolution of remote sensing, sometimes it is not always easy to monitor urban flooding. And then additionally, you also have to see in urban setup what kind of storm water management and drainage systems are in place, because they also play a big role in handling flooding situation. So ARSET is going to provide a introductory webinar on how to combine different data sets, including SAR, to look at urban flooding. But if any of you have experienced urban flooding, or if you are in the business of dealing with urban flooding, how to respond to it, how to monitor it, and if you let us know, that would be great. So the next question here was about WIR's product, and we looked at images from world view, but again, Earth data you can find WIR's data from Earth data. More information can be found from this land processing DAP, and that has a product table, what different products are available. Once you know the names of these products, you can go to NASA data and enter the product name, and then you will be guided to where to get the data. Okay. This is a good question. What advice do you give to small island states? So this is a real issue. If you look at NASA satellite data, the highest resolution is from Landsat, which is 30 meters. Next is SAR, which is, SAR is the highest resolution, about 2 to 5 meters can be there, but both Landsat and SAR, they have temporal frequency, which is 12 to 16 days. So while you can get high resolution in space, you cannot monitor disaster with these satellites or sensors because of the temporal coverage. And so next one is MODIS, which is 250 meters, but that's daily. So there are always trade-off between special resolution and temporal coverage or temporal resolution. So if you are in a small island, then using a model like hydrologic model or flood model would help. For using forecasting, there can be high resolution regional model, and depending on where you are, some information may be available from different regions. Otherwise, there are commercial satellites, they have high resolution data such as SPOT is there, but these data, they cost, you have to pay for them. But if island is really small, then that is really a way to look at the island. It's not free, but then at least you can manage disaster by using this data. But as I mentioned again, if you don't want to use commercial data, then whatever satellite data you have, you can also use some in situ data, and there are a number of ways to downscale data. Maybe that you can try. There are statistical techniques to downscale data to higher resolution. There is no one method that everybody uses, but for your island you can try to regrid and downscale this data based on satellite and in situ measurements. You can use high resolution modeling, that's another way. Yes, that is true. Actually, radar data would give you terrain, and like SRTM is a radar itself. So you you probably can get high resolution terrain, but then again, a lot of processing is needed. So this is 30-meter resolution. SRTM has 30-meter resolution, and we will provide answer to these questions. There is 30-meter resolution in SRTM. This is for question 4. You can, in GIS, you can calculate slope or flow directions. There's a whole digital elevation modeling you can go and find in GIS. You can also find hydrology applications, and then that combining those, you can get information about where inundation might occur. So even in mountainous areas, the limitation is 30-meter resolution, but that's still it's better than having no elevation data at all. So at least this provides you information at that scale. So based on what we saw in these 2 weeks, if you have used any of this data before for emergency management, please let us know, and also let us know if you have used any of these inundation tools before or flood tools before to make any decisions or deal with emergency response or relief operations. If you have participated in any of emergency management, also let us know. What would help is what kind of data are required at what latency, in what sequence would you need data to prepare for an emergency situation like a storm or flood. So if you have this experience, please let us know.